Hello, James Flaten here with the Minnesota Space Grant. Let's talk a little bit about flight data from a high-power rocket flight from a Blue Raven altimeter. So it turns out the Blue Raven will form three files, all in .csv, comma separated value files. So these can be opened with Excel. One of them is called Summary. One of them is called HR, and that one has accelerometer information and gyro information. And one of them is called LR, which has pressure information from which you can get altitude. And that one also shows the various channels, including the apogee channel, the main channel, and the voltages on those various channels. So unlike less expensive altimeters, the Raven 4, and also the Blue Raven, has an accelerometer as well as a pressure sensor and can hence do more calculations. Let's take a look first at the summary file. So basically the summary file, if I double click here, I can open up that column, double click here, open up that column, make this a little bit bigger. This is just the key features from the entire data set, a little bit like an altimeter 2 data logger. So for instance, I notice there's a maximum altitude, 3,300 feet in this case. There's a maximum velocity in feet per second. There's a pad altitude of 1,100 feet, but it says ASL. That means above sea level. So typically, if it doesn't say ASL, that means above ground level. But this particular one is presumably a pressure-based altitude estimate of the launch pad, about 1,000 feet here in Minnesota. And then there's some times: time to burnout, time to fire the apogee channel, time to fire the third or fourth channel if they were in use, for instance. The angle at which the thing ascended originally, which would be basically the launch rod angle. And let's see what I've got here. This is interesting. Horizontal velocity at apogee of 37 feet per second. You can't actually figure that out with a pressure sensor because that only knows about vertical velocity, and this is a horizontal velocity value. So that's probably from the accelerometer sensor suite. Accelerations, perhaps peak accelerations, average accelerations, things like that. Oh, this is very nice. Drogue descent rate, approximately 40 feet per second. Main descent rate, just under 20 feet. That should definitely say 20 feet per second. And then the altitude above the ground, 700 feet in this case, at which it deployed the main parachute. There's some temperatures here. I wouldn't count on the date being correct. You probably have to set the clock in the device to make sure that's correct. Anyway, this is not too different from an altimeter 2 list of data, except it has even more details. I'm not going to make any changes to that. Let's take a look at the LR document. This is the document that has pressure information. So lots and lots of columns here. I notice that if I double click, I can see that column E is flight time in seconds. That sounds very promising. And it starts at minus 1.9. So this device tries to sense a rocket launch, and then it will show you the data from a couple seconds before the rocket launched through the entire flight. So here's a temperature, here's a barometric pressure. Here's called barometric altitude. I like that. That's altitude based on a barometric pressure sensor. So let me graph that by clicking on that column and then control clicking on this column to get both columns selected. Then say insert, scatter chart. Yes. Let me label my axes here under quick layout. I'll just choose the most simple layout, number 1. And that allows me to, let me see if I can just delete that so I don't take up quite so much space for a legend. This will be in, this is time in seconds. And then this is I'm going to just call this sensor value. Should have some units. And the reason is I'm going to use the same graph to show a bunch of different sensors. So let me make the title sensor value versus time and put my initials as evidence that I was the one who made this plot. So what I'm seeing here is as time goes by, remember, if I click on the graph, it'll tell me what has been graphed. And in this case, it's barometric altitude. So this is an altitude, and I see that it starts at about 1,000 feet. That's the level of the launch pad, apparently. Goes up to about 4,500 feet, so about 3,500 feet above ground level. And then it comes down at a fairly constant rate under a drogue, and then it slows down and comes down at another pretty constant rate under the main, and then it levels out. That means it's landed. Oh, I see that there's a couple places where the data seems to give the wrong value for the altitude. I think I understand what happened there. Basically, the lower the pressure, the higher the altitude, it figures. But when you have an explosive charge go off, that pressurizes the inside of the rocket. And if any of that pressurization manages to seep into the av bay, the Raven might, in this case, incorrectly say, oh, you must be at a different altitude, perhaps a lower altitude, because the pressure is temporarily higher. So I think this indicates the firing of the drogue charge. And I think this indicates the firing of the main charge. And if I had a really well sealed av bay, I wouldn't see those two features, but I think I can understand why they're there. If I look across here, this is battery voltage. This is the apogee volts and the main volts. That's good. So here's what I'm going to do. I'm going to drag this over to the column that says apogee volts. And here's what I notice. The volts on the apogee line was 9 volts. And then at about 16 seconds or so, it suddenly went to ground. It went to 0. That's the firing of the apogee charge. And notice it never even really recovered. So this dramatic drop indicates apogee line was fired. And if I go over here, so that was at about 16 seconds, and it looks like the main fired at about 72 seconds or so. If I go all the way back to the altitude, I see that sure enough, at 16 seconds, I reached apogee, so I do want to fire that. And then about 72 seconds or so, I do want to fire the second one, and it might even take a second or two before the main actually comes out and slows me down. So I think I'm understanding pretty much what's going on here. Let me go ahead and take a look all the way over here. Lots and lots of things. And I think I can understand just a couple of them. Let me just take a quick look. Here is where it tries to sense whether you are launching. Here is where it's sensing whether you have reached apogee. Here is apogee being fired. Here's main being fired. These are just columns that indicate when things happened. So for instance, if I take this graph, I'm going to Control C to make a copy of it, and I'm going to stick it over here. And the reason I'm sticking it over here is so that I can see this graph and see these columns. If I click here, it'll tell me what was graphed. And I'm going to grab what was being graphed and drag it all the way over here to the column that's called apogee. Yes, this is just telling me that it sensed that I must have reached apogee at a specific time, and it changed from before apogee to after apogee. So in other words, it says apogee, yes, detected at about 16 seconds. On the other hand, here's apogee fired very shortly thereafter. Here's main fired. Oh, yes, that's about 72 seconds. So in other words, these columns much later in the data record are showing when it made decisions to do various things, if you want to look at that. On the other hand, I think looking at the data showing actual voltages or actual pressures or actual altitudes is probably more useful for data analysis. Fair enough. So that's a little bit about the LR. Let me save that. Save as. Yes, and I'm going to save this as an Excel workbook in XLSX format. And I'm just going to call that with plots because that's what it is. And let's take a look at the other one. So remember those two numbers, 16 seconds, 72 seconds. Now let me go and look at the accelerometer information. So I'm opening up the HR document. This will have completely different channels, not as many, in fact. It still has this flight time. That's useful. And then it has gyro channels for rotation. It has accelerometer channels for acceleration, presumably. And I'm not quite sure what these channels are, but I'm particularly interested in the flight time and the X acceleration. So I control, click. Let me graph that. Insert, chart, scatter chart. So here's what I'm noticing. X in this particular device is along the length of the device. And so if the device was mounted long ways up, presumably the X-axis is the direction of the acceleration. And here's what I see. First of all, I see a big spike of acceleration in the first few seconds of the record. That's the thrusting of the motor. And then about 16 seconds or so, I see a big spike. What that indicates is the rocket just broke apart at apogee, and that shocked the rocket. So in other words, you notice that in the accelerometer, that's when the drogue parachute came out. And then here at about 70 or 72 seconds or something, actually there's a double spike right there. I think the double spike, the first of those two spikes indicates the explosion of the main. And the second spike, about a second or two later, indicates the inflation of the main parachute. The parachute came out and it took a little while for it to actually slow the rocket down. Both of those things indicated a spike in acceleration. And then it turns out that right here, there's a little tiny spike right there. That indicates the rocket hitting the ground and landing. If I were to look at the Y acceleration or the Z acceleration, I will notice similar features, but it's a lot noisier because these are essentially sideways accelerations, not in the main direction of the thrust, for instance. And similarly, I can look at gyro. Is the rocket rotating? And it turns out that once the rocket is coming down under parachutes, under drogue, it rotates a lot. Under main, it rotates some. On the other hand, it doesn't rotate back and forth, particularly early on the way up. It might rotate a bit. In fact, the fact that these numbers are all negative suggests that it is spinning in one direction, but it's not sort of spinning wildly in back and forth directions. That's spinning about the long axis of the rocket. Here is spinning about other axes. And again, I noticed that it's pretty quiet on the way up, and it gets pretty noisy as far as spinning goes on the way down once I'm coming down under parachute. But once it lands, it stops spinning. And so the last couple seconds of this record is after it's landed, and then the Raven automatically turns itself off. So just a little bit about looking at data from a Raven. Let me save that as Excel format, gyro with plots.